Alrighty. Well, as y'all know, obviously, or hopefully y'all got my email that workshop will not be held today. In lieu of that, y'all should have gone over, before y'all went over SN2 and then SN1, and then hopefully you've been over now the two elimination reactions, E1 and E2. Right, so those are the big topics of chapter 6. Now, what I want to come to today is getting over that large problem of you're given. In fact, let me turn this page the other way. Oop. Okay, so you're given this reaction, right? So some generic reaction, and here I've made everything a variable so much as I can to generalize it. So on a test, you'll be given this reaction, and you're told to either you have this and you have these things and you're told to give what is that thing, or you are given the product and you're asked to go backwards to find out what the starting material was. Right? So in doing this, you have to decide whether or not the mechanism for this pathway is going to follow the SN2 route, the SN1 route, the E1, or the E2 route. And for the most part, this can be done rather automatedly. There are certain things in the reaction. There are certain nucleophiles that prefer SN1 rather than SN2. There are certain solvents that prohibit SN1 and SN2 and so on and so forth. So what I would like to do with this worksheet is actually make an algorithm that is a step-by-step set of instructions that you could follow and get yourself to an answer, right? Of course, with all these things, this is a very free-form type of question, and of course, the amount of variations even within itself, even within these generalized variables, are immense. So we're going to come up with an algorithm, and you're going to have to take it with a grain of salt that even though right now that algorithm seems perfect, and seems all-encompassing, it may still not be all-encompassing. And I guarantee you that Dr. Bean has one question tucked away somewhere that will contradict the algorithm. But that's where, obviously, being critical of your decisions and the decisions that we're making come into play. But to get started, I'm going to go ahead and turn this page back the other direction. Let's see if I can rotate that. There we go. I'll give myself a bit more room. So the first thing that's the easiest to depict, to make your decision, is actually this group right here, your substrate. And that's because it only really has a finite number of states. When you're considering your substrate, you really want to consider how crowded your substrate is, and to do that, we've actually quantized that, right? It can be primary, it can be secondary, it can be tertiary, and yeah, so let's just go ahead and delineate all these things. So I'm going to put substrate here, right? So if it's 0th order, and just to be clear, 0th order is a carbon that has a leaving group but has no other carbons connected to it. In other words, it's a methyl. Right, that's what that is. Your textbook would refer to it as a methyl carbon, but I feel like that interrupts the kind of flow of tertiary, secondary, primary, and then methyl. Why isn't that a 0? Right? So it can be methyl, it can be primary, it can be secondary, it can be tertiary, and technically, of course, a quaternary carbon exists, but mind you, a carbon that's connected to 4 other carbons does not have any room for a leaving group, right? So no leaving group, exclamation point. Okay, so we've made a decision, right? We have some sort of RLG. We've identified this, and we can go that way, that way, that way, that way, or that way, right? That's our first decision. How many carbons are connected to the carbon that holds my leaving group, right? Okay, so from here, we've already determined quaternary carbons, no reaction. Actually, NRX, no. I should actually say no and then some other thing, right? No reaction. Right, obviously, because you can't actually have a leaving group. In fact, this decision right here wouldn't even exist. So let's go. If we have a methyl carbon, right? Remember, we're trying to decide between, and I'll put this right here for now, SN2, SN1, E1, and E2, right? We only have four things to decide between. So elimination reactions, remember, they form double bonds, right? So that means that you have to have two adjacent carbons next to each other. So if your carbon is, by definition, not connected to another carbon, in other words, 0th order, that means you can have no E1, E2, right? Cool, we've eliminated 2 out of the 4. Now we decide if it's SN2 or SN1, right? We know that SN1 requires a carbocation to be formed, right? That first step is your leaving group will leave. I should be drawing these out, right? So for SN1, the first step is your, let's see, your leaving group just kind of goes away. And you end up with Lg minus and C plus, right? So your substrate, that carbon, has to be stable with the C plus. And we've already discussed that stability of that carbocation depends on how many carbons are connected to it. And in particular, the more carbons, the better, right? You want more electron clouds around your C plus so that it can share with one another through hyperconjugation, right? And we can actually eliminate this formation, or we can use this to eliminate SN1 from your 0th order and your primary carbons, right? So no carbocations can form on a primary or a 0th order carbon, right? So no SN1. In fact, on this one we can automatically say no SN1. And on these things, usually I would have a giant sheet of paper so that I can put little notes next to everything. I know these pages seem to be kind of cramped at sometimes. So I'll go ahead and try to maybe switch colors. Maybe that will help. Can I switch colors? No, come on. No, that's a highlighter. Ah, there's my color selector. I like blue, right? So C plus. Cannot have that. No C plus. That's my little hyphenated note there. All right, let's switch back. So notice on the top one, you really don't have a choice but to go SN2. Switch back to my pen. There we go. Right, so we have SN2, and there is my answer. Right, so methyl carbons are pretty. So long as you have an leaving group and it's a carbon and you have some sort of nucleophile. Actually, that being said, you have to have a good enough nucleophile for it to kick it off, right? Because even though it's all exposed, your nucleophile still has to be pretty strong. So there's actually one more decision we have to make before we can for sure say that it's SN2, and that is the nucleophile strong, right? Strong. Right, and that's a question. I'm putting a question mark, and that question can only have 2 answers, right? It can be a yes, or it can be a no. If it is a strong nucleophile, then yeah, we can continue with SN2, and that is our answer. If there's no strong nucleophile, then it is no reaction, right? We've eliminated everything else. Oh, there's an X between there, and that's an answer. It's a viable answer. So our product would actually just be our starting material. Nothing would change, right? So for your primary carbon, no SN1. In fact, before I say no SN1, let's go over what E1 is, right? So for E1, you're going to form a double bond, right? One of the double bonds has a carbocation, and let's see, you have your nucleophile right here. But instead of the SN1 pathway, which is your lone pair attacks that carbocation and attaches to it, instead of that, your lone pair is going to attach itself to this hydrogen, and that bond is going to pour into your p orbital and satisfy that positive charge. And I usually get a lot of questions on why the heck would it do that as opposed to just attacking that positive charge. And remember, your nucleophile and your molecules are all floating around in solution. And usually when I think about this, I think of literally just a molecule, a bunch of space, another molecule, a bunch of space, another molecule, a bunch of space. But it really is more like a bunch of dots. They're right next to each other, always rubbing against each other. So at any one point, this nucleophile might be near the hydrogen, or it might be near the C+, and because each they're somewhat reactive, you will have this distribution where sometimes it hits the C+, other times it hits the hydrogen, right? And to be sure, though, the nucleophile would much rather hit that C+. That is a much more energetic reaction, but just sometimes it hits the hydrogen, right? And in fact, because there is this preference, you will get SN1 and E1 happening together, right? Because you have you shared an intermediate. With SN1, right? And the first step of both reactions is the leaving group leaves, forms your carbocation. What's different is that last step, right? Your second step. So right off the get-go, your leaving group leaves, forms a carbocation. You have a choice to go SN1 or E1. SN1 is always preferred because of it's just a simple fact of positive charge attracts a lone pair better than a slightly positive hydrogen, right? So the fact that we can't form a carbocation on a primary carbon not only eliminates SN1, but it also eliminates E1, right? So here we're left with E2 and SN2. Let me erase that. Erase. There we go. Right, so we're left with E2, SN2. Let's figure out what is what. Of course, you have to have a strong nucleophile, so let's put that question in there, right? So strong nucleophile, question mark. Let's go yes, and let's go down to the no. We'll do the rest of these on a separate page, right? The second page, so we have some room to fiddle. Right, well, if it's a no, then it's not a reaction. You can need a strong nucleophile for both E2 and SN2. Right? The difference between E1 and the difference between E1 and E2 is the same difference between SN1 and SN2. In other words, your first order reactions happen in 2 steps. Your second order reactions happen in 1 step. So in both cases, either E2 or SN2, your nucleophile needs to be strong enough to make it happen in 1 step, right? So if it's not a strong nucleophile, that is a G, not a D, I swear, then there's no reaction, right? And that is an answer. That's not a very, it's not a very good answer. It's a good answer. It's just not a very satisfying answer. There we go. That's the question I wanted, or the answer I wanted. Okay, so let's say you do have a strong nucleophile. We're still left with 2 decisions, right? 2 answers to make, right? We can't just flip a coin. Exactly. The difference between the 2 actually depends on how bulky your nucleophile is, right? So we're going to ask a bulky nucleophile. Actually, we need to ask the question, not just bulky. Let's think about the roles of each. For an SN1 reaction, your nucleophile is truly acting as a nucleophile. It's attaching it, or it's truly substituting, right? Well, it is a substitution reaction. It's attaching itself to that carbon, kicking off the thing. But for an elimination reaction, your nucleophile isn't really serving the purpose. It isn't substituting, right? That's why it's not a substitution. Your nucleophile takes the role of a base. It steals a hydrogen and then lets the rest of the molecule accommodate appropriately, right? So the question we need to ask ourselves here is our nucleophile a better base than it would be a substitution, right? Better base. And it might be worth to add a note here, what makes a better base, right? So one thing that makes a better base is a bulkier base, or a bulkier nucleophile makes a better base. So think of the difference between T-butoxide, which is that, versus methoxide, right? And this is a better base, and this is not. And it's because T-butoxide is so bulky. Likewise, think of things like ammonia, right? NH3 with a lone pair. It has that lone pair, so it can act as a nucleophile, right? But if it were to attach itself to something, it would become N+. And it could do some mild hydrogen exchange, and it absolutely could. But it's much easier for it to just grab a hydrogen rather than a carbon. Right? It's more available for that to happen. So in your textbook has some examples of things that might influence whether or not your nucleophile makes a better base or a better substitution. But if it's a better base, then it is E2. And if it's a better if it's not a better base, then it is SN2. Right, and that's the end. Like the ending of our trees are going to be when we can say yes, we only have one answer at this point. Okay. I think the next easiest thing to do would be your tertiary carbons. And we'll move, the secondary is where we have to make a lot of decisions. So we'll go ahead. In fact, I'm going to erase the quaternary one because it's really not even an option. All right, let's just put tertiary right here. And then erase that big ugly line that it is true. Hooray! There we go. Okay. Okay, so tertiary, at this point you are officially too bulky for a substitution, for a second order substitution to happen, right? So tertiary, no SN2. Notice, however, it doesn't eliminate the possibility of an E2, right? And because E2 attacks an adjacent carbon, not the one that holds your leaving group. Right, so we still have that possibility. Obviously, E2 needs a strong base. Your first order products, your first order mechanisms don't. So let's ask that question, right? Do we have a strong base? If yes, then elimination. If no, then we've eliminated okay, so then no E2, right? I'm not going to say it's SN2E. I'm not going to say it's SN1E1 yet, because we still have to consider, does everything else accommodate for that carbocation stability? namely your solvent. You have to have a protic solvent. But if it is a strong base, then yes, we have all the means for an E2. And here we have to ask, do we have a polar protic solvent? In the cases where it's not mentioned, a lot of times we just kind of don't specify the solvent. In that case, just assume that it is accommodating appropriately. Right, so yes, we can have two answers, right? Yes and no. If it's yes, then we can have SN1E1. And I know this is two things, but they cannot happen separately, right? They start with the same intermediate step with that carbocation stability. So if SN1 can happen, E1 can happen as well, and vice versa. Right? And if it's no, then we of course have no reaction. You'll notice probably the most common answer to this is no reaction. But that's just kind of the catch-all for everything. So, yeah. Okay, and then for secondary, let's go to the next page. Oh god, I thought I was gonna skip to the next page instead of scroll down. Okay, so let's look at our secondary. So far we've been using the strength of our nucleophile to determine which reaction pathway it goes, either second order or first order. So that seems to be a pretty good question to ask first. So let's ask, is it a strong nucleophile? Can have two answers, of course. It can be a yes or it can be a no. If it's yes, right? If it's is a strong nucleophile, then we still have, actually at that point we can say no SN1E1. At that point, in the case of no, we can say no SN2E2. Right? If it's not a strong nucleophile, it's not strong enough to do the grabbing of the proton or your carbon and kicking out the leaving group in one step. If it is a strong nucleophile, more than likely it has a negative charge, and forming your carbocation with a negative charge in solution would raise the reaction energy too high to accommodate, right? So we can eliminate those two options. So let's look at the top one, because determining if it's SN2 or E2 is fairly simple. Again, the second order reactions tend to be less picky about your solvent and other reaction conditions. It's for the SN1 and E1 reactions where you have that carbocation, they tend to be a bit more selective. Yeah. Right, so yes, no, SN1, E1, so we still have to decide SN2 or E2. The question, and it's actually the same exact question that we asked before. If we look over here, right, we asked if it was a better base, and if it was, then it chose to be a base, right? So let's go ahead and ask that same question. Better base. If it is a better base, whoops, erase that and go here. If it is a better base, then it would rather do elimination. If it is not a better base, then it would rather do substitution. Right, so at that point we've already decided it is a strong nucleophile, right? So it can do one or the other. Okay, so SN1E1, right? Really at this point we only have one thing to choose, right? SN1E1 really aren't two options. What we're deciding right now is if they can happen at all, right? So is our solvent polar and protic, right? Polar protic solvent We can have a yes answer. We can have a no answer. If it's not, then we get no reaction. If it is, then SN1E1. I'm stopping to think to see if it really is that simple. Oh, so a quick note, right? So whenever we have, whenever we form a carbocation, look for rearrangements. Right, so every time you form that carbocation, check to see if you can do a hydride shift or a methyl shift or a ring opening or something like that to where that carbocation can go from secondary to tertiary or something of that nature. Right, and that comes into play every time we hit an SN1E1 reaction. Right? And I forgot to actually box our end points. Let me try to scroll through this. Yeah, and of course, whenever you do an elimination reaction, let me draw this on the other page. Oh, look at those graphical errors at the top. And then another note right here for elimination. Remember, we're stealing a hydrogen when we do elimination. So one of your adjacent carbons has to have a hydrogen. So let's look at this, right? We have a bromine right there. And let's say we just have two T-butyl things. And then we'll have T-butoxide for an example. Okay, so it's secondary. Cool. In fact, I'll move the highlighter so you can actually see what I'm doing. Oh, can I do it? Nah, that's good enough. Okay, so secondary. This is a strong nucleophile, has a negative charge, so yes, it is a strong nucleophile. Better base, again, T-butoxide is nice and bulky, so yes, it makes a better base. So we can say E2. So now, once we make that decision, we have to be able to follow the E2 mechanism, right? And that mechanism is steal an adjacent hydrogen. So there's the adjacent carbon. Here's an adjacent carbon. Lo and behold, we still have decisions to make, right? If it's secondary, that means we have two adjacent carbons that we could possibly steal a hydrogen from and form that double bond towards. But notice at this point, we don't actually have a hydrogen to steal. No hydrogen. So no E2 can't happen, right? You can't form a double bond right here because then that carbon would have 5 bonds. So just make sure you don't fabricate hydrogens when trying to do these mechanisms. And once you make that decision, follow through with the mechanism and see if it can still happen. And it might be worthwhile for you to do by yourself is instead of making these your final decision, have more decisions to make with regards to, do I have an adjacent hydrogen? Making which bond forms a more stable double bond, right? Because we have to consider Zaitsev's role, and so on and so forth. So this is good enough to get you through the next couple of worksheets, or at least to help you get your head around the decisions that you have to make and to organize all these things in your head, right? This is a great start to that. But remember, if we were able to actually do this for all of the decisions, then this wouldn't be a difficult class, right? So be critical of this. Keep in mind that you may have to make changes later on if you find new information or find an exception to this chain. Or like if you go up the first primary carbon, if you find some exception somewhere, you can of course go back and edit it to accommodate for that exception, and that would be fantastic. Also, obviously, you won't get this to be able to do this on a test, right? You won't be able to get this sheet. So, in my opinion, I'll make the when I took Orgo 1, I made this sheet, and I made it, and I never used it again, and that's perfectly fine, right? The process of you making it is putting it in your head, and that's where it is important. The fact that you have it for reference is actually hindering, right? If you always reference it, then you'll never get it stuck in your head, and on a test you'll be flopping around like a fish. So that's it. I'll see y'all on Monday. Hopefully you all found this useful, and yeah, have fun.